right, here is one example on the topic of conservation of energy. Assume we have a block with mass m attached to a spring to a point. The spring originally has 0 resting length for simplicity, and let's pretend we pull back the mass some distance L and we release it from rest. The question is, what is the velocity or the speed of the block when it passes that x equal 0 mark? So we are dealing with a transition problem, and we have a spring, so there are likely forces involved. Let's draw the free body diagram. This is the mass. I have force of a spring here, force of gravity that way, a normal force holding the mass in place this way. So let's do our, let's summarize what we know and what we don't know. So the given pieces of information in our problem. So we have one state when it is pulled back. We know some information there, and we want to find information at another state. So as always, it's a very good idea to summarize the information you have about these separated states. So let's call state 1 when it is pulled back. What do we know about that state? We know we start from rest, so V1 is 0. I know maybe x1 is minus L, although that is not a very good way to represent here. Let's think another way. Length of a spring is L. This is a better way to summarize the same information, but in a more related way to what we are doing. I have another state I'm interested in, state 2. I know at that time I want to find V2, so this is what I'm trying to find. And I know when I am at mark 0, when x equals 0, that also means the length of a spring is 0. So a spring will become unstretched at that point. I know a few other information. For instance, I know the spring stiffness is K, mass is M, potentially useful. And what else do we know? Oh, resting length is 0. Let's call it L0 is 0. And yeah, that's all my information summarized in a cohesive way. And what I need to find is really this V2. So let's get to solution. I know some information about the state 1. I need to find some information about the state 2. First question is, how is that transition characterized? There are a few different ways you can think about it. I know forces, so potentially I can calculate accelerations. So if I know acceleration, I know the initial conditions, I should be able to calculate the velocities down the road, knowing how much I have moved. But mind that if you do that, this force will be a non-constant force. Force of a spring is related to its amount of stretch. So your force changes, meaning your acceleration will change, meaning you have to take an integral. So possibly doable, but are there better ways? Note that I have information about positions. I know some information about velocities. I want to find velocities. So this, and I don't need any information about time. So this is a well-suited situation to use the work and energy and that kind of space. So I shift my focus to energy. And one other thing I note here is that as my motion is along a straight line, the two forces of gravity and normal force do not do any work. So the only force that does work is the force of a spring, which, surprise, surprise, happy, this is a conservative force, meaning that the entire mechanical energy of the system should remain conserved. So really this transition from state 1 to state 2 or any other state during this motion is characterized by constant mechanical energy. I wrote it that way because I don't have a space. So total mechanical energy is constant, meaning that your kinetic energy plus your potential energy is equal to kinetic energy and potential energy at a later state. So 1/2 mv1 squared plus, for the potential energy, the only source of potential energy that is relevant here is the spring, because my height doesn't change, so there is no change in potential and gravitational potential energy, so I don't bother write that down. So I only write the spring or elastic potential energy. So 1/2 k amount of stretch squared equals kinetic energy down the road, v2 squared plus 1/2 k amount of a stretch later squared. So now I know this, it is 0. I know that. I know this, it is given to us. I know that. I need to find this one, so that's my desired variable. I know that, and I know this one is 0, 2. Because I passed the same 0 point. So just put the numbers, all the halves cancel out. In this case, good. So that is 0. I have KL1 squared on this side equals MV2 squared on the other side. So my V2 becomes I call this L. I didn't call. Yeah, I called it L. And it is the square root of K over M times L. Right? I hope so. Something looks weird. Let me double check. The units. So whenever in doubt, do the. Looks good. So K is Newton per meter, square root times meter. And Newton is force equals mass times acceleration. Oh, not meter, kilogram. Kilogram meter squared per second. So kilograms cancel out. 1 meter here, 1 second there. Where is my meter squared? No, not meter squared, kilogram meter. Okay, all good. Meter second squared. So everything cancels out. Only the square minus 2 remains. So the units are good. So everything is good. I'm happy. All right. So this is how you can use the conservation of energy to solve for relationship between movement and speeds when all your forces are conservative.